Hello.
Hello, how are you?
Oh, good. I've never spoken about Cosmos to a group of Access folks.
Yeah,
Good morning. Great. Out here in
great.
Wisconsin. Great day to be outside.
Yeah, it's beautiful, isn't it?
I'm by Madison, Wisconsin. It's you pick your times to battle the weeds. Morning in the 60s is great.
Yeah, yeah, really.
Tend to my little vineyard too, so there's that. It's that time of year.
Oh, vineyard meaning grapes?
Meaning grapes.
Oh, cool.
That's a little
Like,
R&D.
fermented grapes?
I've got a couple of table, but the rest are, yes, for making wine.
I'm not going to put my video on the whole time here, but I don't know if you can see my earrings here. I've got little grapes. You probably
Amazing
know.
you wore your grape earrings today.
Our grape earrings, and I wore my Microsoft Access shirt here.
Ah,
So welcome today. We're having the season kickoff for the 2023-2024 season of Access Lunchtime. And today for our speaker, we have Leonard Lobel. Did I pronounce it right? Lobel. Okay. Leonard is a Microsoft MVP in the data platform space and the Chief Technology Officer and co-founder of Sleek Technologies. He's also a Microsoft consultant at Ernst & Young. Leonard, why don't you go ahead and take it away?
Well, thank you so much, Maria. Again, just want to make sure everyone can see me and hear me clearly as well as my screen. And if so, I'll just dive right in. So this is an introduction to Azure Cosmos DB, and I am presenting this to a group of folks from the Microsoft Access space, which is quite a bit different audience than usual. We are dealing with a database technology that is radically different than Microsoft Access. So in addition to my kind of like prepared slides that I normally have for presenting this session, I prepared a special individual slide to kind of help us bridge the gap from the outset between Access and Cosmos DB to help better level set prior to actually diving into the content of the session. So Maria, thank you for that lovely introduction. Again, my name is Leonard Lobel, and I run my own company back in New York called Sleek Technologies. I am a consultant with Ernst & Young, data platform MVP, do lots of speaking and writing. I have a tremendous amount of detailed content on Cosmos DB available on Pluralsight. If what you hear today in this brief session piques your interest, you can dive much deeper and get much more information by visiting Pluralsight and checking out any of my courses there. And with that, there's some contact info. If you want to reach out to me, I'd love to hear from you. And with that, we can just jump right in. Here's that kind of like level setting slide I was mentioning. Most of us are familiar, or all of us here are familiar with Microsoft Access. We know this to be a single desktop engine, meaning that there is an instance of Access, which is an instance of the database engine, the query engine, etc., on each client machine, all of which share a single database stored on a file server and is a relational database. So familiar concepts of normalization and joins and SQL queries, but their SQL queries execute on the client while the data resides on the shared server. And so this is suitable only for relatively small scale scenarios because, of course, the engine has to process all the data on the server, even if it's only going to return a few rows. There's a lot of latency and a lot of network traffic involved there. So that doesn't really scale very well. And so the next step up, and it's a fairly straightforward migration path, would be to SQL Server, which I'm guessing many of you folks are also familiar with. All of the same concepts of a relational database apply. We have tables, joins, and foreign keys, etc. But only the database engine resides centrally on the database server. I meant to change this label here to say database server. And where we have like MDF files, which is similar to an MDB file, it has the data, but the engine itself resides centrally as well. And so this makes for a much more scalable solution. However, how scalable? How many users? This database server, which let's just say database server, We can add more RAM and we can add more disk, but up to a point. I mean, there's only so large a machine can grow before you hit the ceiling on these resources. And that's where the concept of a NoSQL distributed database comes in Cosmos DB, which is what we'll be talking about today. So the clients connect to a centralized database service, which is massively scalable because they're not dealing with a database server. They're dealing with a container, which is a logical entity that stores all of our data. And behind that container, or within that container, if you will, transparent to us, are any number of servers that are needed to manage the scale and growth. If done properly, you have literally unlimited scale, unlimited growth available. All right, so with that level set, let's jump into our overview of Cosmos DB and talk about like this term NoSQL and what it is, because it's like a really bad term. How it got dubbed, I'm not sure, but it's not to be taken literally. SQL is a language. L in SQL is for structured query language, and there's no reason you cannot apply some dialect of SQL to any kind of database system. So what it really means is how we handle big data. It's just kind of a buzzword for how we manage big data. Typically identified by the 3 V's, volume, velocity, and variety. Volume is just how much the sheer volume of data. Velocity is what is our request rate, how many clients are hammering away at our database within any given period of time. And variety relates to schema in the sense that, we're accustomed to defining columns inside of tables and setting a certain schema, but often it's difficult to manage situations where we have a rapidly evolving schema and just managing the type schema of our database. You have one server, a database server, it can grow, you can add more disk, you can add more memory, but at some point you're going to hit the ceiling. At that point, what is really the only way that you're going to continue to scale is to scale out, as opposed to scaling up. So not just one server, but 2 servers, 5 servers, 10 servers, 1,000 servers, whatever's needed. Really kind of giving you no upper limit on how you can scale. Of course, the idea is you don't want to have to manage this yourself, and that's what Cosmos DB is going to do for us. So understanding what NoSQL means is really to handle the challenges of big data as identified by the 3 V's. Well, first of all, a NoSQL database is going to be distributed. There are going to be multiple replicas of your data to ensure that you have high availability. If one replica goes down, then another replica is available, and this gives you resilience. You're also going to get this scale out that I started describing. There's just going to be more nodes added to the cluster to manage the growth of your data and your demand. And this gives you elastic storage and throughput. And it's schema-free. So unlike what you're accustomed to in Access or SQL Server, where you define columns and data types, etc., none of that exists in the world of NoSQL because the database is schema agnostic. You don't have to define or enforce a schema, and the database is happy to accept data in any shape without doing like an alter table, add column, or etc. I was just describing NoSQL databases in general. There are several. There's MongoDB, there's Cassandra. There's quite a number of NoSQL databases out there. So in the case of Cosmos DB, well, this is Microsoft's massively scalable distributed database. I used to define it as Microsoft's massively scalable NoSQL database, but very recently, Microsoft actually added a component to Cosmos DB that also gives you the relational world. We're not going to refer to that because that is a bit of an edge case. And for an introduction to Cosmos DB, let's just focus on the core of what Cosmos DB is. So it's a distributed NoSQL database. It's fully managed on Azure. The platform as a service, you don't have to manage it. You get 99.999, that's 5 nines of availability service level agreements. So that's like kind of a marketing buzzword that translates in practical terms to a guarantee. Well, if there are 4 nines of availability, 99.99, that would mean that you would be guaranteed in a year you would never have, well, you'll probably have 0 minutes of downtime, but you'll never have more than 52.56 minutes of downtime. And if you do, you start getting a refund on your Azure bill because it's a service level agreement. And you will get 5 nines of availability if you globally distribute your database, if you allow your database to exist not only in one Azure region or data center, but multiple. And that will give you 5 nines of availability with a guarantee that you will never have more than 5 minutes of downtime per year. And that's a pretty nifty guarantee before you start getting your money back. And it's extremely fast in terms of point, reads, and write. So if you have a type of scenarios where your use cases, reading and writing individual documents, but there are tons and tons and tons of them, and it grows and grows and grows, you will be able to retrieve individual documents within a single-digit millisecond. That means 10 milliseconds or less to read and write these documents, no matter how large your database is. You will get automatic horizontal partitioning, whereas, like as I explained, new servers will be added to handle the growth and demand, not just for the growth in terms of storage, but the growth in terms of demand, i.e. throughput. Global distribution is a key tenet. If you need your data globally distributed, you have a global consumer base, your applications are distributed worldwide in various regions. If your data is only located in one place, then the farther away your application centers are from the database, the greater latency you will have. But Cosmos DB gives you very simple, very easy to implement point-and-click geo-replication. Literally by clicking on a map in the portal, you can distribute your data globally and get those 5 nines of availability. And you can even allow multiple region writes as well as reads. And so, and a write operation to any one data center will be automatically geo-replicated to all the others. And there are conflict resolution options as well as you might imagine. Finally, and this is kind of probably the hardest part to wrap one's brain around Cosmos DB when they're first getting started, is this concept of multi-model, multi-API. It started out in its early days exclusively as a document database, and by document, I mean JSON document database. In later years, they added other APIs so that you can treat these kind of key value pair items, which a JSON document is a collection of key value pairs. But you can view that collection of key value pairs also as a table, not a typed table, but I'm talking like a schema-free table like you have with Azure Table Storage, or a graph if there are many relationships, columnar, and most recently, actually, relational. And we'll talk a little bit more about that. But how can one get started? Well, there is a 30-day free trial. You need a Microsoft account, which I'm guessing most of you have. Here are the links you would need to get one, as well as to get your 30-day free trial. There is also, the normal way is to use the Azure portal if you have an Azure subscription. Like the 30-day free trial does not even require an Azure subscription. But if you have an Azure subscription, there is a free tier where you get roughly the first $64 a month free. And if you're just playing around, you're not going to reach that limit, because that is going to give you 25 gigs of storage and 1,000 request units per second. And I know that sounds like a foreign language statement I just made about 1,000 request units per second. What does that mean? It's a measure of throughput, okay, in terms of demand, right? That you will get. You'll get the first chunk of throughput and that first chunk of storage for free. You are allowed one free Cosmos DB account per subscription. Once you use it, you won't be able to use it again. You'll have one account. And there's also a local emulator that you can download, which doesn't even require an internet connection. It emulates the service fairly well on your desktop machine. So let's jump into a demo and see how we go about creating a Cosmos DB account. And we start off in the Azure portal, where you will click on the hamburger menu and choose to create a resource. And then you can search for and find Cosmos DB, Azure Cosmos DB right there, and pick it. There's these other like kind of pre-configured versions of Cosmos DB, but if you want to just kind of configure it, like kind of from a vanilla starting point, then you would choose Azure Cosmos DB right here, hit create, and you're off to the races. This is the opening page for creating a new Cosmos DB account. This is the most confusing part of Cosmos DB. This is coming back to the idea of this multi-model, multi-API. We are going to focus exclusively on this for this session. This is also known as the native API or the core API. In its earliest days, this was the only option. And what this gives you is a container of JSON documents that you can actually query with SQL, even though this says NoSQL. So I said NoSQL is a bad term, because SQL is just a querying language, and there's certainly no reason you can't implement a dialect of this language, SQL, to work against a non-relational data store. And that's what we're going to be focusing on. You see these other options? Let's just forget Postgres for a second, but there's MongoDB, which gives you MongoDB compatibility. There might be any number of reasons why you would choose MongoDB, Cassandra, or Table, or Gremlin. Gremlin is if you're working with graph data where relationships are a very key part of the data. Maybe if you even have more relationships than entities, then that could be a good choice. But all of these, except for PostgreSQL, are NoSQL key value store, where we're going to focus on this one, where the key value item is a JSON document that we can query with SQL. Most recently, Microsoft added this and really took what was already kind of hard to kind of grapple with and make it even harder, because this is a relational database. Like all the things that I said, NoSQL wasn't. It does have a type schema, and it uses foreign keys and joins and foreign key constraints, etc., just like SQL Server does. But it has a special distributed engine, because remember, these relational databases, they scale up. They're difficult to scale out. But there's a special Citus open source extension that makes it possible for Postgres. So that's all I'm going to mention about that, because I don't want to take something that's confusing and elaborate on it when ultimately we're going to just focus on this core API, also known as the native API, also known as the Azure Cosmos DB for NoSQL API. Too many names for the same thing. But once we make that selection, you go through the process of choosing a subscription and a resource group. If you're not familiar with Azure, this is just an Azure concept where you can store your items in groups. And you can create a new one, or you can pick an existing one. In this case, I'm going to go with Cosmos DB Demos RG as my resource group, where I'm going to store a new account that I'm going to give the name Lenni Demo. And if you look here on the right and you see the green check mark, you will see that that name is available, because I need to pick a name that is no one else has chosen. It's got to be globally unique. You'll see that this name is embedded in the part of a URI or a URL that points to my account. And under this account is where all of my Cosmos DB databases and containers and JSON documents will live. And I'm also going to choose a location, which is going to default to West US. And there are many other options, like a capacity mode that we'll talk about more. Provision throughput is the more common approach. There's global distribution that I can set up right here at account creation time, but of course I can do it later. There are network security options like firewalls. There's automatic backups. There's encryption options. All of these things, or most of these things, can be changed later. So I'm just going to go ahead and hit review and create, and then see that it's estimating 2 minutes approximately to create this account. So I'll hit create, and because I have pre-recorded this, we won't have to wait those 2 minutes. The deployment will run, and then roughly a few minutes later, it will be complete, and you'll be able to click to go to the resource. And now here I am in the Lenni Demo page in the Azure portal for the Lenni Demo account that I just created. I start off in the Quick Start tab, but let's just pop up to the Overview tab. And there, have a quick look and see, well, first of all, you can see, because I chose West US, those are my only read and write locations. But once we globally distribute, you'll see more locations there. We can also see, if I just scroll down a bit and choose keys, in this URI, this is the endpoint. This is that URL that I was telling you about that you can navigate to or point to. And it's my account because there's the Lenni Demo that I chose at https://accountname.documents.azure.com on port 443. That's always going to be the URI. And then these set of master keys. And you need to think of these as like super privileged administrator accounts that you certainly don't want to share with folks. You have to click the icon to actually view them. There is a primary key and a secondary key. This is the master key. In order to connect the Cosmos DB, you will need the URI and a master key, where the master key could either be the primary or the secondary. And the reason that there are two is simply because you can easily rotate them while keeping your system up. So those are the two things you always need to provide. And depending on the client that's connecting, or the SDK or the NuGet package, you might be asked to supply the URI and the master key as two separate values, or you might be asked to supply a single connection string that has within it both the URI and the master key. It makes no difference. So just think of it as the only two things you need to connect. There are other options. There's integrated security with Azure Active Directory beyond the scope of this session, but this is the simplest and most direct way out of the box. It's available if you have access to the URI and the master key. You can connect, right? There are those two components. All right, let me flip on over to the Data Explorer, where you can see that we have no data yet. And that makes sense since we just created this account. There wouldn't be any data yet. So in our next demo, we're going to create a container. Right? And also define what is a container. So we'll hit new container. The container is something that lives within a database. So like in Access and SQL Server, you have a database, and then you'll have multiple tables within that database. Well, in Cosmos, you'll have a database and multiple containers within that database. However, the reasons why you would create multiple containers within a Cosmos DB database is very different than the reasons you would create multiple tables in an Access or SQL Server database. Because the reason in that scenario is, you have a different schema. You have a set of columns that define a customer or an address or a product or an order. So you create a table for each of those things. In Cosmos DB, you don't create a container for each of those things because in Cosmos DB, there's no schema, right? There's no predefined schema. You can have one container that stores all of those different entity types. So then why would you ever have more than one container within a database in Cosmos DB? The answer to that will become apparent once you understand the key characteristics of a container. And we're going to talk about what those are. We don't have a database yet, so we're going to create a new database called families. This is a bad default option. I'm going to uncheck it. You can see share throughput across containers. What that means is right down here, this is database throughput. There's an option for Autoscale and manual, and then there's a number here that you can plug in. And we're going to talk about what all of that means. But what we don't want is for this to be set at the database level. We want these values for Autoscale, manual, and this number here to be set at the individual container level, not shared across all containers. So this is a poor default. I'm going to uncheck it. You see that when I uncheck it, those options disappear, but they actually reappear further down here at the container level, the Autoscale, manual, and the numeric input. We'll talk about what those are when we get to the container. But meanwhile, I've just created a new database called families. This is a super simple example. So I'm only going to store one type of document, a document that represents a family in this database. So I'm also going to call it the container families. And now I need to talk about how I am going to partition this container. This is the key critical concept in Cosmos DB, which if you get it right, you will achieve that unlimited scale. It's suggesting the ID property. I'm going to choose instead the zip code property, which is nested beneath address in a JSON structure. We'll talk more about this partition key, but ultimately what it means is that all families within the same zip code, they're going to be kind of clustered together physically within a partition, within a logical partition. And addresses with different zip codes will be stored in different partitions, and we'll be able to scale out to as many zip codes as we need. Scrolling down just a bit, now we'll get to those options that started off at the database level, and I unchecked that bad default, and now I have to make a decision here for the family's container. Do I want Autoscale or manual? I'm going to explain all this in detail. So for now, I'm just going to choose manual. And when I choose manual, I'm expected to provide the number of request units per second, which I will also talk about in a moment. I'm going to leave it at the lowest value, 400, which is also the cheapest value, which you can see is ultimately going to cost just under $24 a month. All right? And go ahead and make those selections, scroll down a bit. There's an analytical store option that's beyond the scope of this discussion, but you can enable it for real-time analytics in Azure Synapse. That's an advanced topic. Let's just keep it basic, create this container within a new database by clicking OK, and now we see the families database. Expanding it shows the families container within that database, and expanding that shows our items, which are our JSON documents. Scale and settings options, if we want to raise that 400 RUs per second, that's where we would go. And things like store procedures, user-defined functions, and triggers, which are server-side objects that can run logic on the server side, that is within Cosmos DB, rather than on the client. So now we've created our account, we've created a container within a new database. The next logical step is to store some data, creating documents or items. They both mean the same thing. So I'll go to items, and we're creating documents there, right? Go to items and click new item. And you can see that Cosmos DB is giving me this. Now there's a number of ways to get data in here. And you might be wondering, how do I get data from Access into Cosmos DB? Well, it's more than just about moving the data. It's also about reshaping the data, as you'll see when I kind of like break out this document. Because what I'm going to do is, you see, it's suggesting that there's an ID property. So yeah, it's schema-free, meaning that this JSON document can have any properties, and I don't have to predefine a schema, and it'll be accepted. But there is always one required property, and that is the property called ID, plus the property that you chose as the partition key, which, if you recall, was the zip code nested beneath the address. That would also be needed. I'm going to replace all that with this JSON document, which you'll notice is actually missing the ID property. Now, the ID property is required. So the way the Azure portal works is, if I don't provide it, it's going to generate a GUID for me. And here is my zip code. Here is my zip code property. This is my partition key. So this document is going to be in the 60601 partition, since I chose the zip code nested beneath the address as the partition key. And when I hit save, you'll see that that ID property did get generated, like I mentioned it would, with a GUID. Plus, you'll also see these other kind of scary looking, but really relatively unimportant system properties, all of which begin with an underscore. Most of them you'll never have to interact with. Notable is the timestamp. That TS stands for timestamp, and that is a value that represents the current time. This is the number of seconds elapsed since, I think it's January 1st, 1970, known as an epoch value. It's a timestamp. All right, and you can see here that the ID and the address and the partition key value for the item that I just created. I'm going to create another item. And this time I'm going to add a pets property that didn't exist in the previous document. So two things should be very, very apparent about how radically different this is from either Access or SQL Server. Number one is, I didn't have to define a schema. And when I have a new property, I can just include it. I don't have to define it. And number two, you'll see that I have an embedded arrays here, where, to make it fit on the screen, I just made them, there's two simple strings in this array, but this array could have two objects in it. And in the relational world, or let's say even, like in Access, you would have two separate tables and a foreign key relationship between them. But here, I've gone ahead and embedded them. So the modeling concepts are radically different as well from what you're accustomed to. Now I've got two different documents. You'll notice my second document is in a different zip code. You can see the partition key is different. These two documents live in two separate logical partitions. The last demo that I'll show before jumping back into some of the other conceptual slides are how to query documents. I mean, that would be the next logical step that you would want, right? After loading up a few documents into your container, you might want to hit new SQL query and try a few of these out. Like, show me all documents where the city property that's nested beneath the address property is Chicago. And we know that's both documents. This C is an alias for the current container. So it can be anything. It's going to be the family's container. We go ahead and execute it. And you can see I get back my two results. Now, this is what we call a cross-partition query, because we understand that both of these documents live in separate logical partitions. Behind the scenes, they're aggregated and they're returned as a single result set, but it is less efficient than when you actually provide the partition key as part of the query, and that's part of what helps drive your decision as to what you'll choose for the partition key. Your most common queries, which in our case, if our most common queries are going to be by zip code, that's why zip code would have been a good option in this case for the partition key. Here I'm retrieving all documents with a given zip code. We only have one because this is a small demo, but I could return 100 or 1,000, and then even filter within that zip code on other criteria, but it would be a single partition query, very efficient query, because the partition key is known. And here I get my one document. And functions like is defined, because I know one document has a pets property, the other one doesn't. There's no enforced schema. Well, maybe I just want to get the ones that have a pets property. That goes ahead and gets that one document that has the pets property, but not the other that doesn't. JSON documents, there's no guarantee that there's even going to be a property called kids. But if there is a property called kids, And let's say there is a property called kids, there's no guarantee that it's an array because you can have two documents with a property called kids in each, and one is an array and one is a number, right? Because without having an enforced schema, it's the Wild West. It could become chaos. You have to manage the chaos that can otherwise ensue. But assuming that the document has a kid's property and assuming that the kid's property is an array, we're going to get all those documents where there are more than two elements in that array. And that, in this case, is going to give me this one document because there's 3 children in that array. So those are kind of like the main demos. I'm going to just jump ahead now to discuss some management options, how you go ahead about managing Cosmos DB. Well, you can use the Azure portal like we saw, right? You can create accounts and use the Data Explorer to create databases and containers like I just showed you. And then there's also the Azure CLI. This is a command line interface. You can install it locally on your machine, or you can access it as a cloud shell right inside the portal by clicking in the toolbar and getting this prompt. And now I'm in a command line where I can use the syntax where I define a few variables. In this case, I want to create a new database. So I'm going to call Azure Cosmos DB SQL Database Create. I need an account name, a resource group name, and the name of the new database, which I've defined in these variables. And just goes ahead and this confirms that it's been created. If you're a PowerShell person, similar concept. I'm doing exactly the same thing here. I'm creating a database by defining a couple of variables and calling the new Azure Cosmos DB SQL Database commandlet that's available for PowerShell. And it goes ahead and creates the database just the same. ARM templates and Bicep templates, these are Azure concepts for deploying any kind of Azure resource. There are other ways that you can go about deploying Azure Cosmos DB accounts. And ultimately, at the end of the day, everything boils down to the REST API. Like, here's an example from the documentation that shows a post, which in REST means a create, and the URI is /DBS, means I want to create a database, and here in the header, I've provided the ID of the new database that I want to create. I give like a 201, which is successful, which means the database was created. This is the last resort. REST is the last resort. If you're a .NET developer and you're doing C# or VB.NET, you're going to want to go with the .NET SDK, which will shield you from having to set up these headers. It gets pretty tricky with the authorization headers. You don't have to worry about any of that if you use the .NET SDK, which we'll see a little bit of, I think. And that is the first major section of this presentation, which looks like I'm only about 2 or 3 minutes over where I wanted to be at this point, so I think we're doing pretty good. Throughput and cost. This is all about performance. And let's talk about what those RUs are, the request units per second, and the difference between latency and throughput, because those are the two ways that we measure performance, right? There's latency, which is really the perceived performance. How long am I waiting from the time I issue a request until I get a response, or how soon after I give the waiter an order for my burger, so does the burger show up at my table? And then there's throughput, which is very different. It's like how, within a given amount of time, how many requests can it be executed? This is the perspective from the kitchen, which can only produce so many burgers within a fixed amount of time. And if you want more burgers within that amount of time, you're either going to have to hire additional chefs or purchase additional equipment, right? So latency is about how far away I'm sitting in the kitchen and how long it takes for the waiter to walk back and forth. And throughput is all about the perception from being inside the kitchen. There's only so many burgers I can produce. These are two very different things. So let's talk first about throughput, and then we'll talk about latency shortly thereafter. For throughput, we use this term request units. You saw this RU acronym where we provision 400 request units per second of manual throughput when we created our container. But what does that mean exactly? RU is a blended measure of all of these hardware metrics. So instead of thinking in terms of how much memory you're using or how much CPU your request is consuming or how many IOPS are involved, there's just going to be a number of request units that are consumed based on all of these hardware metrics. Because, of course, all requests are not going to be equal. Writes are going to cost more than reads, always. Because when you read from any available replica. When you write, well, you have to update multiple replicas. You have to update indexes potentially. So it's going to cost more for writes than reads. And even within reads, complex SQL queries are going to cost more than simpler SQL queries. The concept that I mentioned before of cross-partition queries, where all the partitions in the container have to be checked because you didn't supply a partition key, that is definitely going to cost more than a single partition query where, let's say, the zip code is known, as we saw in the earlier example. So there's all these variables about how much a request is going to cost, but the request units themselves are deterministic. So if you execute the same request multiple times, it's always going to cost the same number of RUs given the same data set. So we also saw this manual and autoscale option. It had defaulted to autoscale, but I changed it to manual and then went with 400 RUs per second. That's if you do provision throughput, which is what we did. There's also a serverless option, by the way. You can create an account to go serverless where you just pay by the request, but you also don't get those service level agreement guarantees. If it's a small scale, grandma's recipes, small little demo that rarely runs, serverless could be a more cost-effective option. But within provision throughput, there are these two choices of manual and auto scale. So let's go through them. Let's look at manual first, which is what we went with. We chose manual and 400 RUs per second. What that means is that you are guaranteed at any point in time, it's like pre-provisioned, it's pre-allocated, so whether you use it or not, you're kind of paying for it. That within any given second, you can request up to 400 RUs. And if you exceed that, it will be throttled. Now, you are provisioning 400 RUs, and whether you use them or not, you're paying for them. So what you want to do is you want to raise and lower this as needed. So if I set it at 5,000 RUs per second because I need consistently 5,000 RUs per second, this would be what it would look like. If it is a scenario where the demand goes up and down, the throughput requirements go up and down, and it's predictable, like I know on the weekends, or I know like when there are certain promotional sales, promotions that go out, I know the request is going to go up, so I can kind of predict when this thing is going to go up and down. If I can predict when it's going to go down and I don't lower it, I'm going to be paying for the 5,000 RUs of unused capacity. So I would lower it to 2,500 when I know that's all I need, and then raise it back to 5,000 when it becomes busy again. That's if it's predictable. If it's not predictable, you can go with autoscale. And when you go with autoscale, which is the default, here you're choosing a maximum number of RUs to be provisioned. But that is just the maximum. It's actually going to be anywhere between 10% and that maximum. So in this case, between 400 and 4,000. And it will scale up and down automatically from the max that you choose to 10% below that max. So here, it's not predictable. I don't know when it's going to go up and down. The best that I know is that at most I'll need 5,000. So I'll choose auto scale, set it to 5,000. And what I'll get is, of course, 10% of that is 500. I will get anywhere between 500 and 5,000 RUs a second, depending at any point in time. Of course, I'm still paying for that 500 RUs even if I'm going to be completely idle. So this is still not appropriate for every scenario, but that's why we have serverless, which I mentioned. You just pay by the request. It's a consumption model. 1 terabyte max. It's a separate account, but you only pay for the RUs that you use. And it looks something like, now you might think, well, if I went with autoscale, shouldn't that work? It'll work, but again, if you're idle most of the time, you're always going to be paying for that 10%, which doesn't sound ideal. And when autoscale raises the throughput, because it detects that it needs to, it raises it for an hour, and you pay for that hour. So for real kind of like spiky workloads, where it's just going to be a request here and a request there, that's not appropriate. There's going to be unused capacity while you're idle and during that hour, which is why you want to go with serverless. Like every request, whatever it costs, that's what you pay. And when you're idle, you pay nothing. Provisioning container throughput, like I said, how many request units per second are going to be available, and what happens if you exceed that? Your requests will be throttled, as they put it, which is just a polite way of saying you'll get an error, right? 429. Right here, you can see it. Too many requests, and a recommendation for how long to wait before retrying. And if you think about just putting retry logic, we'll talk about that in a moment, but here in code, here you can see I'm creating an item inside of a container. And that's the document that I'm trying to create, and that is the value of the partition key for the new item. But if it fails with a too many requests, which is a 429, then I can catch it in the catch block. Too many requests. Now, you might be inclined to just add some retry logic, but you are using the .NET SDK here. And under the covers, the .NET SDK, if you look at the HTTP traffic behind the scenes, you'll see that the SDK has already retried multiple times and have gotten 429s multiple times before raising the exception in your code. So just adding more retry logic is only going to further degrade the user experience. Instead, you need to address, why am I getting so many throttle requests? Why am I getting so many 429s? It's going to be for one of two reasons. You either simply need to raise the throughput and pay for more, or you didn't model your data right. You didn't pick the right partition key, and there are things that you can do to lower the number of RUs that you're consuming so that you don't get these throttled requests. There's a capacity calculator that can help you understand or predict up front at a high level how many RUs you might need. Here's a quick demo. You just go to this link, and for the default settings, you see that it's broken down between storage and throughput. Storage is the cheap part. Like for 10 gig, you're only paying $2.50. But for the lowest amount of RUs, which is 0.008 cents per 100,000 RUs per second that you pay each hour, times 400 RUs, it's going to be like $23, and it's going to be about $25 for that container. But if I go ahead and plug in some values here, like I expect I'm going to need 1,000 point reads and 200 creates, 50 updates, stuff like that, and I hit calculate, I'll get an estimate of 147 RUs per second. So that takes on to our section on horizontal partitioning. It looks like I've totally caught up. This is where I wanted to be at this point. Horizontal partitioning is this key concept that I started explaining that you get in order to achieve elastic scale. So partitioning is the way that you achieve that massive scale out within a container. We understand that a container is where you store your JSON documents. This is a single resource. It's just a logical resource because behind it, physically, there are multiple so-called physical partitions. You can have multiple of these fixed capacity. Think of them as individual servers, if you will, that can scale out on demand and transparently, split a partition that is becoming too full into a new partition and continue scaling out automatically within a container. So we have a single container. We read and write documents in and out of that container, but behind the container, there's a cluster of these so-called physical partitions identified by these black boxes. And you can have more, and you can have more, and there's no virtual upper limit to how many physical partitions you can have in a container. And each one of these physical partitions, again, think of it like a server. Each one has disk storage and CPU power for throughput. So if you partition your data properly in a manner that allows it to kind of like uniformly scale out infinitely, this design will give you both unlimited storage and unlimited throughput. So I refer to these black boxes as physical partitions. I also told you to think of it as a server, although it's actually a little more than that. Under the covers, each one of these physical partitions is a unit of replication, where each one of these is replicated 4 times, at least, within a single data center, even if you don't globally distribute. And the reason that there are at least 4 is that if one fails, you still have 3, and you need 3 to have a so-called quorum or majority, where if you have 2 replicas that commit the write, then the quorum majority can identify that as being the most current version of the data. But for our intents and purposes, just think of each one as a server or as a physical partition. So what's a logical partition? Well, let's zoom in on 3 of these physical partitions to understand what a logical partition is. When we write a JSON document to a container, it is going to land on any one of these physical partitions. But how does Cosmos DB know which physical partition to store each of these documents, or to store or retrieve each document? And the answer to that question is with logical partitions, identified by these blue dashed lines. So these documents are organized in logical partitions, and that's defined by us. Remember, when we create a container, we have to choose that all-important partition key. That's what defines a logical partition. We chose the zip code, but let's look at a social networking scenario. Let's say you're creating a Facebook or a Twitter type application that has a scale massively and it has users and posts and comments and likes, I might go ahead and choose the actual username as the partition key to let this database massively scale. And what that would mean, and let's just forget about these physical partitions and focus just on the logical partitions. And if I go with the username, it would mean that all of Tim's documents live together in one logical partition, all of Andrew's in another logical partition, and so on and so forth. Because in this world, there's no concept of joins, and there's no concept of foreign key constraints. So, logical partitions in a way kind of joins all these documents. All of Tim's documents are joined together because they live in the same logical partition. And it's going to be very efficient to retrieve any user's documents, no matter how many users you have. And each of these documents could be of different types. This could be the one document that describes Tim, let's say his profile. These next several documents could be some of Tim's posts that Tim created. Some of these documents might be likes, or where Tim has liked someone else's post. Some of them might be comments, where Tim has commented on someone else's post. And each of these documents have a different schema, which in the relational world or in the world of Access would mean like different tables. But here, they're all stored together because we're schema-free inside of a single logical partition. It's important to note, because we saw how we had arrays where you can embed child entities within a parent entity using arrays. There's only so much you can cram into one document, though, and that's 2 megabytes. Once it doesn't fit in 2 megabytes, it has to spill over. And ideally, it would be like it at least lives in the same logical partition so that they're joined. And that's based on the partition key that you choose. And you can have 20 gigabytes per logical partition with no limit on the number of logical partitions. And that does give you a limitlessly scalable database. The beauty and the magic of Cosmos DB is in its partition splits. Here I've got a container with 2 physical partitions with a bunch of documents spread across, each of them living in different logical partitions based on our partition key. And at some point, one of these partitions will become too busy. And by busy, I mean one of 2 things: either too full, the storage is overflowing, or the demand, the throughput, is too high for the RUs that you provisioned and are therefore paying for. So it could be well before you run out of disk space that Cosmos DB will split this into 2 physical partitions so that you have extra CPU power to handle the throughput that you're paying for in terms of the RUs per second that you provision on the container. And it'll just spin up a new physical partition. It'll move roughly half of the logical partitions over from the partition that's being split without disturbing any of the other physical partitions, and everything goes along its merry way. And it all happens instantaneously, without interruption, and without any disruption whatsoever. So what you want to do is avoid these so-called hot partitions. This is not a pretty picture. This kind of picture kind of indicates that I've chosen a partition key that does not uniformly scale very well. And I've got a hot partition on storage here. Most of my documents are stored in one logical partition. That's a hot partition. This looks better from a storage perspective, but it could still present a hot partition in the form of throughput. So because if I choose, let's say, the date instead of the username, and most of our queries for the current date or the most recent dates, well, then all of the requests are going to hit this logical partition because the older dates are not going to get hit as often in my use case and for my application. And the way the cost works is that the throughput that you provision for a container and pay for, and therefore pay for it on your Azure bill, that throughput is distributed evenly across all the physical partitions in the container. So in this example, with the 3 physical partitions, had I provisioned 3,000 request units per second for the container, that means each physical partition gets 10,000 RUs. And that means I'm paying for 30,000 RUs, but I'm really only getting 10 because these 2 are radically underutilized. So that's a hot partition on throughput. And that's, again, why username makes an ideal partition key here. It's evenly spread across all users. Users are equally queried. And this will just scale indefinitely. We talked about cross-partition queries already. We understand that if the partition key is known to the query, in this case the username, this is going to be a single partition query. Cosmos DB will know how to route this query to the specific logical partition, no matter how many others there may be. It'll very efficiently get all of Mark's documents or any subset thereof. Like if I just want to get Well, it marks documents within a date range or of a particular type, like just as comments or just as likes. All of those would be very efficient single partition queries. It would know how to route the query to which logical partition and therefore which physical partition, no matter how many it may be. This is a seemingly equally innocent looking query, but the username is not known. I want to query all users and only get those whose favorite color is red. Well, what's the partition key? It's not known. So the query has to fan out, and this will happen automatically and transparently in the background. You don't have to do anything special. You just don't want this to be the most common type of query. You want this to be the exception to the rule where you have queries like this. Most of your queries should know the partition key, but if you don't know the partition key, it's okay. It'll fan out, which means it has to hit every physical partition. And it's obviously, and then it'll aggregate the results and give them to you as one, so you don't have to do anything, but obviously it's going to cost more. It's going to be more intensive. So if most of your queries are cross-partition queries, that becomes a problem. If only a few of your queries are cross-partition queries, it's not a problem because the cost of hitting a partition and not getting any documents back is only one RU. And if it doesn't happen that often, you'll never feel it. You'll never feel an RU here or an RU there. But if it's queries that are like high volume, high velocity queries that are pounding and pounding and pounding your database with great frequency, then these cross-partition queries will present a problem. You need to choose the right partition key to avoid, to make sure that most of your queries are single partition queries. You need to base it on your most common usage pattern. Like in most cases, if I know the zip code, that was good for the families example, or if I know the username, that's good for the social networking example, so that you get this uniform distribution, not just of storage, but throughput, request demand, as we've seen. One very interesting thing with Cosmos DB is that most other NoSQL databases don't provide as transactions using store procedures where you can update multiple documents and have them either commit together or roll back together. And that's a very powerful feature, but it only works within a logical partition. So that's another consideration. If you're updating a user and a user's addresses at the same time, and you want them to commit as a whole, you want them in the same logical partition. Which brings us to our last and final portion of today's presentation. I'm just going to go for a few more minutes to talk about global distribution and then open it up for questions. Actually, before I jump into there, because Maria did make an interesting point to me before the session when we were chatting. If you're thinking about how you would go about migrating access to Cosmos DB, I think that you would need an intermediate step to first migrate from access to SQL Server, which is very straightforward because it's tables and columns and foreign keys exactly the same in both environments. And then use Azure Data Factory to migrate from SQL Server to Cosmos DB, because it's not just about moving the data over, it's also about transforming it, right? Like taking some of these entities that are in two separate tables and putting them into one document with a nested array, like maybe putting addresses as a nested array within customer, where in your Access database, they're in two separate tables. Azure Data Factory will let you do that. I actually walk you through an example of how to do just that on my Pluralsight course. So go ahead and check that out if you're interested. So our last topic is global distribution, which is all about replication. So why do we want to replicate? Performance is an obvious reason. If you have multiple replicas, you're going to get better performance. You can, right? Because you can have all of your demand and your requests serviced by a set of replicas, also giving you high availability in case you have one failure. And in the case of global distribution, then you're replicating across regions. That's going to bring the data closer to the application that the consumer is connecting to. Again, remember I mentioned that even if you don't globally replicate, you're going to get 4 replicas of each physical partition, even within a single data center. Also, business continuity. I mean, you could have, like I said, within a region, one of those replicas might fail, and you'll have automatic failover. But globally, one would never hope it shouldn't happen, but you could have a natural disaster, a major failure, and the entire data center goes down, and you will have business continuity if your data is replicated in other data centers as well. And there are many of them. This is a relatively recent picture, but it's constantly expanding. So how do you enable it? It's so simple. You get this point and click map in the portal. Here I've got these 2 regions that are checked, or 3 of them actually. Just point and click. And if you enable multi-master, then you're also allowing each of these regions to accept write operations as well as read operations and have them geo-replicate. So here I've got, I started off in West US when I created the account. Now I'm adding Switzerland, North and Southeast Asia, and I'm enabling them, and I'm also enabling them for writes. A quick demo and we'll be done. Let's say I stand up a Cosmos DB account in West US, and I've got an application running there. And for this demo, it's just going to be a VM, but it would normally be some sort of app service or some website that's running, that's using Cosmos DB as the backend. Presumably your consumers are in West US, and so they connect to the application server, and when the application server needs to read and write data, it does so against the West US Cosmos DB instance extremely rapidly with a single-digit millisecond access, as you can see in this pre-recorded demo that hasn't been doctored in any way, but you can see that each request came back in under 10 milliseconds. That's what I was saying earlier about single-digit millisecond access, just to read an individual document. In this case, it was a query, and you see that even though there was some variance in the latency, which is very, very low, because I've chosen a seat right next to the kitchen, if you will, to use that analogy. So it goes back and forth very quick. But the cost to create the same burger in each case is 2.97 RUs. Now, what happens if I stand up an application server in Southeast Asia so that my Southeast Asia customers are close to an application server, and let's say using something like Azure Traffic Manager to make sure that your Southeast Asia customers connect to this application server? Well, the data still resides in West US. So the reads and writes in this case, running the same demo in this scenario, what you will see is a much poorer performance. Compared to the West US consumers, the Southeast Asia consumers are taking an eternity, relatively, in hundreds of milliseconds to query the same data, query the same document repeatedly. Although notice the cost to make the burger, once the request gets to the kitchen, after the waiter has traveled back and forth from Southeast Asia to West US, it's the same. As far as the chef in the kitchen is concerned, it's 2.97 RUs to create that burger. However, if I enable global distribution, Cosmos DB will automatically replicate. It'll stand up an instance in Southeast Asia. And in each region, we'll use the instance that's closer to it. Consumers in both locations will enjoy the same single-digit latency, high performance. And you will get automatic failover. So if a data center goes down, well, in this case, I've only got it replicated in 2 regions. It'll automatically fail over. But without going down, you'll just see the higher latency suddenly while you rebuild or repair this instance to bring it back online. But if I had more than 2, if I had multiple, it would automatically home in, it would zone in on the closest proximity available to handle requests in a failover scenario. So with that brings us to the close of the hour. I want to thank you for attending. Here's my contact info. I appreciate your attendance, and I would like to now maybe pass over to you, Maria, and to open it up for questions that folks may have.
Thank you so much. So before we actually do questions, since we are almost at the hour, I'm going to go ahead and just make a brief announcement. I just want to talk briefly about our topic for next month. Access Lunchtime is the last Tuesday of every month, at least during the August to May timeframe. We usually take a break in the summer. So the next session is the 29th of September. And for that, our topic will be accessibility is for everyone. And we're also going to have a Q&A where you can meet the new Access Program Manager. So the talk itself, the first half of the talk is going to be about accessibility, specifically in Access, but it can apply to other types of applications as well. And that's going to be by Tom Van Stiphout, Kim Young, and Linda Lucanen. And you know, or may have heard that Linda Lucanen has recently been announced to be the new Access Program Manager. So she's not only going to give part of the beginning section talk, but then the last half of the talk will focus kind of on a Q&A and some introductions from her. So please join us again next month for that. So meanwhile, I'm not sure if we have any specific questions in the chat. Crystal has asked, I don't know if you want to ask directly, Crystal, or if you want me to read out from the chat. Okay, I'll read, Crystal. So she says that it seems like Cosmos is more geared to enterprises with deeper pockets. It also seems like one could benefit from a database like Access to manage your partition keys. Good point. Yeah, so...
I actually don't get that second point. I get the first point, which I can respond to. But what was that about using Access to manage your partition?
She was joking that it's important that you keep all those keys someplace, and of course you do have.
You don't need to, but you don't need to manage the keys.
Yeah,
you just need to pick the right key, and everything is self-managed. To the first part of the question, though, yes, Cosmos DB has established an unfortunate reputation as being expensive. Now, of course, it can be expensive. If you're on a smaller scale, well, first of all, there is that free tier. So if you fit within those whatever the disk capacity and those RUs, it doesn't cost a dime, right? And there is also a serverless option where it only costs per request. So in both of those cases, for smaller scale scenarios, Cosmos can be very cost effective. But I would venture to say that the primary use case is for these large scale where you need the ability to grow infinitely. Especially if you're ingesting things like IoT telemetry data, when airplanes that are in the air or delivery trucks that are on the road that are emitting, or sensors for temperature or whatnot, and you're ingesting that at a very rapid rate. You're not going to be able to load that into your Access database or your SQL Server database. So there are certain scenarios where you just have to go with some sort of massively scalable database. But for small scale scenarios, Cosmos DB can still be an option and not cost that much, and you can still enjoy the benefits of a schema-free, a schema-agnostic database platform.
So one question I have, and another user alluded to that in the chat, I have connected an Access front end to an Azure SQL backend. That same connection string that you have a copy button to on one of your pages, I just basically copied that and I replaced my table link with that connection string, and it worked seamlessly as a linked table. Has anyone here, or have you heard of anyone try that with an Azure Cosmos DB? Something similar as far as connecting to Access?
Well, not from Access. I got to say, I don't believe that there is any direct connectivity from Access to Cosmos. Like, it's kind of like linking, if you will, like a linked table as you're describing.
Right.
What you can do in SQL Server is use a feature called Polybase, which is a way of kind of materializing non-relational data into virtual tables. Right? It's called data virtualization. So it's like create table. It's create external table, where you point to your Cosmos DB database. So it's almost like a linked server, but it will transform the JSON into tabular, so that you just select from that table like it's an ordinary table in your database, an internal table in your SQL Server database, and it'll just return the data. Obviously, the performance goes down because it's going across the wire and doing the transformation every time you run the query, but it's effectively the same as a linked server, but you can't do that from Access, to my knowledge.
Okay.
Sorry.
It's all right. Neil asked, similarly to Azure SQL, how do you predict how many transactions an application is likely to use?
That's the hardest part, right? Like predicting. You saw the the pricing calculator that where, you plug in these numbers, like I think I'm going to need 200 RUs per second. That has to be based on some kind of expectation or prediction that could be wrong. First of all, the more you use Cosmos, the more you get a feel for what things cost. Like I said, it's predictable. The same query is going to cost the same RUs every time. And you always get back the RU cost in the header. So as you start getting more familiar with Cosmos DB and more experience with it, you get a feel for what things cost. But if you do plug the wrong numbers into the calculator because you need to plug in larger numbers, hopefully the only ramification is that you just need to raise the RUs, and not that you discover, well, I've chosen the wrong partition key, because ultimately it seems like most of my queries are cross-partition queries, and that would be a poor design choice. And I encourage you to check out Pluralsight, my Pluralsight course on data modeling in Cosmos DB, where we take AdventureWorks, which is a relational database from SQL Server, and we refactor it for Cosmos DB, trying to take those predictability questions in mind in the process. But yeah, the short answer is it's not easy to do.
Crystal asked, what is the advantage of Cosmos over SS? And I assume she means SQL Server, besides distributed storage. And I would kind of expand on that. Besides the size and the distributedness of it, are there like certain data models that it's better to go one direction versus the other?
Yeah, so here's the SQL Server Cosmos DB comparison, where we are still dealing with a scale-up architecture. Now, on Azure, there are distributed solutions for relational, but they are very, very difficult to implement. Meanwhile, the distributed capability within Cosmos DB is something you don't even think about. It's kind of built in behind the scenes, doesn't require any expertise. And this will scale literally infinitely if you partition your data properly. And whereas this will not. If you're dealing with very high volume scenarios, either ingesting IoT telemetry, or you're, an Amazon.com, a massive e-commerce site where it's not just hundreds of thousands of people hitting your website, but also other APIs that are integrating with your database that are issuing requests. That is something that you could easily see a SQL Server falling short in terms of being able to keep pace with that scale, where Cosmos DB will gleefully scale.
Okay. And Jack mentioned that there's actually an ODBC driver for Azure Cosmos.
Oh, is there?
He's got a link there in the chat.
Yeah, I actually have heard of that. I haven't explored it. There's also
to BI and data analytic tools. Very interesting.
Yes, very.
Normalize data with SQL queries.
There's also a framework provider that does a similar thing using a framework for Cosmos DB.
Yeah.
I'm not familiar with
I have to play with it a little.
Mm-hmm.
I do know that your bit about ingesting lots of data, I've heard use cases, for example, with, where you've got like some kind of machines that monitor specific things, and then you need to later report on specific data out of those big streams, those large streams of data that come out of stuff like that. And I totally heard you say this is a great use case for that. So
certainly is. Although normally the events don't go directly into Cosmos DB. So when you talk about ingesting a large amount of data, you could be talking about investing a large amount of data because you're just migrating a lot of data, so it doesn't kind of matter how long it takes. And then there's ingesting a large amount of data in real time, like as these sensors are emitting temperature information, or the delivery truck overheats, and it's constantly emitting that data and ingesting the data in near real time and keeping pace with the flood of events that are coming in. That's where you're going to see Cosmos DB shine. Oh, but what I was going to add to that was that when the stream of data is coming in, normally it'll flow through Stream Analytics, because you can do a lot of aggregation and real-time operations as the events occur without ever persisting the data to the database. And you don't even need Cosmos DB because there's Azure Stream Analytics for that. But normally in IoT scenarios, when airplanes or delivery trucks or devices are emitting data, that data is received with IoT Hub, which is a wrapper around Azure Event Hub, sent to Cosmos DB, possibly with Stream Analytics in between, to maybe aggregate some of those events before pushing into Cosmos DB. And then in Cosmos DB, the thing about storing in Cosmos DB, it's a database. It has a SQL querying language. You can query this thing using a rich SQL dialect, which is something that you normally can't do against things like data lakes or other massively scalable storage platforms.
We have one more question here in the chat. Jack asks, is there a method to report on all the data types being stored, like we would do in SQL, for example, to list tables and fields? Like, can you get the schemas out of
discovering the metadata? Yes,
yeah.
100%. Like within the SDK, you can say, okay, point to an account and say, discover what databases are in that account. And for each one, discover what containers are in those databases. And for each one, discover that containers throughput, partitioning, partition key, and other characteristics of each container. All that metadata is available as you would expect.
Great.
There's one thing you can say about Cosmos DB is it's transparent.
Anybody else have any questions? Feel free to unmute and ask, or that's from HSON. You mean JSON? Through JSON? So Crystal asks if that's from JSON, and I don't, if I understand her question right, I don't think that's what you're implying. That's not, the metadata doesn't directly come from JSON.
Well, it's going to be returned to you in JSON. I have demos that show that, where
it'll be in that format.
Things get projected out as JSON. They're not stored physically as a JSON, like the way you might think of opening Notepad, typing some JSON and saving it. Yeah, it's not stored that way. It's stored in a more kind of primitive key-value format known as ARS, Atom Record Sequence, and then it gets projected out as a JSON document. Whether it's your data or this so-called metadata about databases, tables, and schema information. Bad word because there's not that much schema.
Right. Okay. Yeah, I think that clarifies. If not, Crystal, if you want to rephrase the question. Does anyone else have any other questions for Leonard?
I think you did a very good job, Leonard, and you're right. It's a different way to look at things.
Thank you. Well, hope you have a better idea of what it is. Maybe one day you'll find a use for it, and you'll have a head start with understanding its kind of core concepts.
Well, and I think most of us think of ourselves as database people, and it's always good to learn about different types and understand why somebody might want to use one type versus the other. So I think that in itself, it's been well worth our time, I know, and I appreciate the time that you've given today here. Thank you very much.
Thank you for inviting me. I hope to see you all again someday.
All right. Thanks.
Thank you.
Thank you all. Have a wonderful day.
Thank you, Lenny.
You're welcome. Thank you.